Alice Shapley visiting us today. I've known Alice for a long time, and just to give you a recap of her history, she was undergraduate at some small northeast universities in Cambridge. What's it called?
I don't know, I don't remember.
I think it's called Harvard or something. And then in 1997, she made the worst mistake of her career. She decided instead of coming to Santa Cruz, she would go to some second-rate Southern California school for grad school. I think it's called Caltech. Yeah, and then she went out to Berkeley to be a Miller Fellow. Then she went to Princeton as faculty. Decided she didn't really like the cold weather. Perhaps some of her colleagues, I don't know. Anyway, I'm just kidding. And she decided she wanted to get back to California, understandably, and took a tenured position at UCLA. And Alice is definitely an expert in high-redshift galaxies. She really makes major contributions to this field. And I'm so thrilled to have her here. And pay attention because she talks even faster than I do. And she can probably get the information of 2 colloquia into 1. And so please just welcome to us.
Okay, thanks, Bea. Thanks so much. Thanks a lot. Thanks for such a nice introduction. Yeah, okay, so today I'm going to talk about the rest frame optical spectra of galaxies and how this is a window into how galaxies form at redshift 2. So let me start off by talking about my collaborators. So to point out several other faculty at the University of California, Mariska Creek, Naveen Reddy, Brian Sienna, Allison Coyle, Brian Wolfwasher, and then some of our grad students, Bill Freeman, Ryan Sanders, Sedona Price, and Laura Jacobs. Okay, so this figure here may not mean anything to you, but I promise you by the end of the talk, we'll talk about exactly what's going on here and all the wonderful things you can learn from it. Okay, so if you're like me and you worry about galaxy formation, here are some of the big questions that you might think about. So we want to understand what are the physical processes driving star formation in individual galaxies through cosmic time. How are stellar mass and structure assembled in galaxies? So we want to understand about the relative importance of the buildup of stellar mass just through the process of star formation versus the assembly of galaxies through merger type events. We want to understand how galaxies exchange gas and heavy elements with the intergalactic medium. And also, another really important question is, what is the nature of the coevolution of black holes and stellar populations? And as I'll talk about today, rest frame optical spectroscopic observations across various cosmic epochs will address all of these questions. And in particular, right now, we're at a really special time for rest frame optical spectroscopy. There's some wonderful new developments that I'll describe that really make it a great time for trying to address these questions. Okay, so just a little background. Our understanding of the galaxy population in the local universe has really been described wonderfully by massive redshift surveys like the Sloan Digital Sky Survey and the 2-degree field redshift survey. So they give a detailed description of the local galaxy population and tell us about the endpoint of galaxy formation. What do galaxies look like now? And so these surveys have imaging of many more, but more relevantly for today, spectra of about a million galaxies. And with such imaging and spectra, we've obtained an understanding of the distribution in luminosity, color, mass. By mass, I mean stellar mass, dynamical mass, black hole mass, structure, gas content, metallicity, environment, and clustering. And so you can see some plots here from the Sloan Digital Sky Survey. It's a little bit cut off, sorry. So not only do we know the distributions of these properties, but we also know how they're connected. Okay, so galaxies show many very strong correlations among their properties. And so these are some plots from a review by Blanton and Moustakis. You can see, I don't know how well the labels came out here. This is a distribution in luminosity, color. These are a couple of structural properties, the Sirsic index and the size of galaxies. And you can also see in the off-axis plots how these properties are connected with each other. If we wanted, those are photometric properties. We can also see some properties based on spectra. The 4,000 angstrom break is a measure of stellar population maturity. This is the gas phase oxygen abundance. This we'll talk about later on in the talk. This is just a measure of the dynamical masses of galaxies with the velocity dispersion plotted against stellar mass. Okay, so this is the type of information that you get from a massive survey like Sloan, what the galaxy properties are and how they are connected. Okay, so this tells us now, but for the full story, we need data from earlier epochs. And there are several spectroscopic surveys that probe out to redshift 1, like the Deep 2 survey, the VLTV Most Deep survey, the Z-Cosmos survey, the Primus survey. So these are spectroscopic surveys that have sample sizes of maybe 10,000 to 100,000 galaxies. And these samples have shown what the evolution is like in luminosities and masses and colors and sizes and environments of both star-forming and quiescent galaxies. So redshift 1 corresponds to about 8 billion years ago. We see relatively smooth evolution in the star formation rates and structural properties of galaxies, and not that much evolution in the population of quiescent red galaxies. So we have a couple of examples here. This is from the Primus survey. This is from Moustakis et al., showing the evolution of the stellar mass functions of both star-forming and quiescent galaxies. So the red ones are the quiescent ones, the blue ones are star-forming ones. And you can see, for example, that actually the dashed line is the low redshift sample. There's not that much evolution in the massive end of the quiescent galaxy. Stellar mass function, there might be some more evolution at lower masses. Now, the bottom plot is from Faber et al. We also have an expert in the room who's done a lot of stuff about the evolution of the luminosity function. But this also shows the evolution of the luminosity function of both red galaxies and blue galaxies. And I think there's some consensus about roughly how much stellar mass is assembled by redshift 1. It's at least about 50% of the local stellar mass density of the universe, maybe more. And so, this is interesting to get this description of the galaxies out to redshift 1, but I would argue that the next frontier is really going to higher redshifts. Okay, so looking at higher redshifts between 1.5 and 3.5. This redshift range hosts the peak of both star formation and black hole accretion activity in the universe. So you can see here on top, this is a plot of the star formation rate density as a function of redshift from Reddy et al. You can see that there's a peak here between 1.5 and 3, where the star formation rate activity is at least an order of magnitude higher than it is in the local universe. And the bottom here, sorry, the horizontal axis is cut off. What we're showing here is from Hopkins et al. The evolution of, basically this is the volumetric luminosity density of quasars as we view it as a black hole accretion rate density in the universe. You can see that it also peaks around redshift 2. Okay. Now, there are some qualitative imprints of the local galaxy population already in place by redshift 2. For example, there is some evidence for a bimodal distribution in galaxy colors. Okay, so this is from Casada et al. The vertical axis here is rest frame U minus B color. The horizontal axis is stellar mass. And you can see here, this is a histogram of the colors. And you can see out to redshift 2, it does really look like there is a bimodal distribution of galaxy colors and a red sequence. So you might say, okay, well, the galaxy population is showing a lot of the patterns that it does, that it shows in the local universe. But there are also some pretty important differences among the galaxy population at these early times, because we're talking about 10 billion years ago. So this is a plot that shows what the stellar populations look like of galaxies at the high mass end of the stellar mass function at redshift 2 from Creek et al. This is a plot that has spurred many plots in a similar fashion, where you actually plot the data point for each galaxy as its HST image in the rest frame optical. And so I want to call your attention to this range here. This is above 10 to the 11 solar masses. And what you can see is that, so these are all the most massive galaxies at redshift 2. There are plenty of red ones, but there's also quite a diversity in the morphologies and stellar populations. U minus B tells you about the specific star formation rate, this star formation rate divided by stellar mass. Okay, so the point is that massive galaxies are not all dead at these early epochs the way they are in the local universe. There's some other big differences. If you look at the dynamical properties of rotating galaxies at redshift 2, so you can tell this by doing some IFU spectroscopy to make a map of H-alpha emission of a star-forming galaxy at redshift 2. You get the line of sight velocity, you also get the velocity dispersion at each point. So this is an example of a rotating galaxy at redshift 2.17. So you can see this is the line of sight, this is receding from us, this is approaching from us. You can see there is some shear, velocity shear. But on the right here, you see this is a map of the local velocity dispersion. And if you look closely at the color map, you can see the local velocity dispersion ranges from between 50 to 100 kilometers per second. This disk is very puffy, okay, and turbulent compared to the thin disks that we see, like our Milky Way galaxy, in the local universe. And this is a very common phenomenon, these very turbulent, clumpy disks in these early times. Also, if If you look at the overall distributions of star formation rates as a function of their stellar masses, this is what extragalactic astronomers have recently termed the main sequence of star formation, for better or worse. And the point is that if you look here at the plot of star formation rate versus stellar mass going from low redshifts to intermediate redshifts to the epoch we're talking about, redshift 2, what happens is the specific star formation rates of galaxies, the rate at which they're forming stars for a given stellar mass, is elevated by a factor of several, okay, as you go to these earlier times. So galaxies are much more active. Furthermore, we don't have too much time to talk about today, there's evidence for ubiquitous large-scale outflows of material from galaxies at these early times. Okay, so definitely, this is an interesting epoch because, the galaxies have not all settled down. We can potentially learn a lot about what goes into forming these patterns that we see among the galaxy population at lower redshifts. Now, the issue, though, is that most studies of galaxies at redshifts greater than 1.5 are based on multi-wavelength photometry at photometric redshifts. Okay, like for example, this plot that I just showed you has a lot of data points on them, but the vast majority of these data points are based on just photometry. Until recently, spectroscopic studies of the early universe were really dominated by rest frame UV observations using an optical spectrograph of UV-selected galaxies. So such studies are weighted towards relatively blue star-forming galaxies. Now the rest UV has a lot of wonderful information in it. There's a whole other talk that I could give about all that you can learn from rest frame UV spectroscopy. But it tells you something. It tells you about massive stars, it tells you about the cool part of the ISM, it tells you about outflows, and that's what I'm showing here. Is I'm showing a couple of examples from Steidel et al. Of some rest frame UV spectra. So these were taken with the LRIS spectrograph on Keck. These are a couple of composite spectra. So we're probing the rest frame range. You can see the range in angstroms from 1,000 to 1,600. And we see features like Lyman alpha. These are metal lines from the interstellar medium that often show evidence for large-scale outflows. The continuum is dominated by the light from O and B stars. This is a stellar link line. Okay, so this is telling you a lot of information, but it's not sort of telling you about, the bulk of the stellar population, the gas and the dust in the H2 regions. For that, you really need to go to the rest frame optical, okay? Sort of bread and butter spectroscopy on which our understanding of the local universe is based. Furthermore,
Lyman alpha is in emission. Why is Lyman beta in absorption?
Well, I think the Lyman alpha is in emission because I think the question is, I think it's not that surprising that the Lyman alpha is in emission.
No.
I think the cross section for scattering for the Lyman alpha is greater, so that when you have these large scale motions, the Lyman alpha photons can actually escape because they get scattered to larger velocities relative to the ISM. Maybe the Lyman beta doesn't get as much diffusion in velocity space as the Lyman alpha. So there are plenty of spectra where you actually just see Lyman alpha in absorption. But the emission tends to be in cases where there's some kind of velocity offset of the Lyman alpha line. So it's getting out to oceans in the ISM. So the thing is that these studies here, so not only are we learning about just the massive stars and the cool face of the ISM, they're also weighted towards, as I said, these rest frame UV selected galaxies. So if you really want to get a more unbiased view of the galaxy population, it's with all sorts of galaxies, with galaxy types, it's really a good idea to go to longer wavelengths. Okay? Selecting galaxies in the rest frame optical, and then doing rest frame optical spectroscopy. So there have been some nice developments in terms of understanding the rest frame optical spectroscopy of galaxies, especially recently with the deployment of the Wide Field Camera 3 on the Hubble Space Telescope in 2009 and the infrared GRISM. There's some new surveys of maybe up to about 10,000 galaxies with rest frame optical GRISM spectra for a wide range of galaxy types. This is an example from the 3D HST survey from Grammer et al., where you can see O3 and H beta and some other lenses for a galaxy redshift 1.77. But the problem is, and it's the 3D HST survey and then the WISP survey. These are two big projects that have been using these infrared GRISMs. The problem, though, is that these GRISM spectra, they have limited resolution. So the resolution of R of 130 means that velocity resolution is greater than 2,000 kilometers per second, which means that you're not resolving, lines except for maybe the broadest lines from AGNs. And furthermore, there's limited wavelength range, so the GRISMs cut off at around 1.6 microns. Have a limited window here. So these are limitations of these GRISM observations. At the same time, going back more than 10 years, there are samples of moderate resolution spectroscopy in the near infrared, or with the rest frame optical at redshift 2. So by moderate resolution, I mean resolution of more than 1,000, so that's a couple hundred kilometers per second. But the problem is that these samples are small, and typically they're only done for one filter at a time. Okay, so I'll show you an example of such spectra. This is a sample of about 100, this is a subsample from this set of 100 galaxies that we covered with the NIRSpec spectrograph on Keck. So this is just basically one band, though. It's a K band covering the H alpha emission line. That's what you're seeing here. These are H alpha lines. The horizontal axis is microns. Here is around 2 microns. So we're covering H alpha. Sometimes we also see nitrogen 2 and sulfur 2. We'll see more examples of this. Okay, but the problem is that these samples are small, and yeah, just typically for one filter at a time. Okay, and so we can only, when you only cover one filter at these redshifts, you're really only getting typically 1 or 2 of these rest frame optical features. And so what I want to tell you about now is what's all the great stuff that you can actually learn from these rest frame optical spectra. Okay, they're chock full of information, but not all of you may be familiar with everything that you can do. And so I wanted to give you sort of a tour of the great stuff that you can learn from rest frame optical emission and absorption lines, because that's what we're going to be doing. The main emission lines to keep in mind are oxygen 2 here, H beta, O3, this is H alpha, nitrogen 2, and sulfur 2. And the ratios of these emission lines are used to infer a very wide range of physical conditions. Okay, so like for example, if we want to start off sort of basic, the Balmer lines, H alpha and H beta, can be used to estimate star formation rates. This is a very basic proxy of what's going on in the galaxy. And so another thing that's really important is understanding the oxygen abundance. Okay, so the gas phase oxygen abundance in galaxies. Okay, so that's a proxy for the past metal enrichment of the galaxies due to the previous star formation, built up in the stellar population, and modulated by gas inflows and outflows. And there are various ways that astronomers have for trying to infer this gas phase oxygen abundance using combinations of these strong emission lines. So there's one common one called R23 that's based on the sum of these oxygen lines divided by H beta. You can also, if you only have one band, you can do something like N2, which is the ratio of nitrogen 2 to H alpha. It turns out this isn't a bad metallicity indicator. You can use more lines, like you can use these ones divided by these ones, or you can use the full set of strong rest frame optical emission lines, comparing them to photoionization models to try to infer the gas phase oxygen abundance. This is turns out it's fairly controversial, as we'll talk about later on. Now, there are other physical properties you can infer, like the density of electrons in star-forming regions based on either the oxygen 2 doublet ratio or the sulfur 2 doublet ratios. These are both doublets, and it turns out the ratio of these doublets is sensitive to how dense the electrons are. You can also learn something like the ionization parameter, which tells you about the overall ionization state of the H2 regions. It's determined by the relative density of ionizing photons to particles. And one empirical measure of this is the O3 to O2 ratio, and some other assumptions. And one of the sort of holy grails of studying rest frame optical emission lines is trying to determine the temperature of the H2 region based on the ratio of an auroral line. You can barely see it, it's very faint, 4363 relative to the stronger oxygen line, 5007. If you can determine the electron temperature, then it turns out that you can actually just say for real, based on atomic physics, what the abundance of oxygen is, rather than using these other indirect measures. So this is a very sort of attractive quantity that astronomers try to measure, but it turns out to be extremely challenging. And of course, if you want to make full use of those Balmer lines for estimating star formation rates, you do have to know what the dust extinction is, right? You have to, dust is very important, especially at these early times, and so if you want to try to estimate dust, you look at the ratios of these Balmer lines, which you can predict, again, based on atomic physics, assuming what the temperature is in the H2 regions. You know exactly what these ratios should be, and then deviations from the ratios tell you about how much dust there is. Okay, so that's another really key measurement. And you might think, oh, well, that's obvious. That should be done easily. It's done wholesale for hundreds of thousands of galaxies in the local universe, and it turns out it's been done for almost no galaxies at these redshifts. All right, so this is our full sort of suite of strong rest frame optical emission lines, O2, H beta, O3, H alpha, nitrogen 2, and sulfur 2. So this is the spectrum of a fairly, blue star-forming galaxy with very strong emission lines. You can see if you look at an earlier type, you can see that the ratios are different. Okay, so this is a wonderful code for trying to infer a very large range of physical properties. Now, there's more that you can do, okay, but wait, there's more. You can also look at the dynamical properties of galaxies based on the widths of these emission lines, the velocity dispersion of a line like the H alpha emission line, right? So if you have a size estimate for the galaxy, some idea of its geometry, you can use the line width to estimate the dynamical mass. As we might have time to talk about later on, you can also use the pattern of emission lines to try to discriminate between whether an active galactic nucleus or massive stars are the source of the ionizing radiation field that's giving rise to these emission lines. And furthermore, you can study things like the large-scale outflow properties of the galaxies. These emission lines here, like H alpha, give you a really good proxy for the systemic velocity of the galaxy. And then if you recall, I showed a couple of examples of rest frame UV spectra. You can measure offsets between the redshifts of these UV absorption lines and something like H alpha emission, and that tells you, that gives you evidence for large-scale motions in the galaxies. You can even use, if you have high enough resolution spectroscopy of the H alpha line so that it's actually resolved, you can actually look at the detailed profile of the H alpha line and try to look for deviations from Gaussian and see is there evidence for large blue shifts in H alpha emission, which is another signature in outflow. Okay, so these are some of the things that you can learn from rest frame optical emission lines. But you can also, of course, learn a lot from absorption lines in the rest frame optical range. So, for example, at low redshift, the Sloan Digital Sky Survey has shown what the power is for using diagnostics like the 4,000 angstrom break and the equivalent width of H delta absorption to learn stuff about the mass to light ratio of galaxies, the fraction of the stellar mass that's been formed in a burst, the stellar velocity dispersion, the metallicity. So let me point out a couple of these diagnostics. So the 4,000 angstrom break, this is an example from Kaufman et al. Showing a younger galaxy and an older, the spectrum of a younger galaxy and the spectrum of an older galaxy. And the 4,000 angstrom break is just defined as the ratio of the flux longwards of 4,000 angstroms to shorter of 4,000. These windows didn't come out that well. But the idea is here you can see in the older galaxies spectrum, there's a bigger break right around 4,000 angstroms because the light is dominated by later type stars. And the Balmer lines, so this is H delta here. This is H delta here. The strength of the H delta absorption line, which tells you about the contribution of A stars, tells you about how much of the mass has been formed in a recent burst. The thing is, okay, while these measurements have been made wholesale in the local universe, okay, the thing that I need to impress upon you is that the sample of objects for which such measurements have been assembled at redshifts greater than 1.5 or so is really in the handfuls. Okay? So it turns out that continuum spectroscopy, like in order to measure absorption lines, you need to have a continuum. Continuum spectroscopy at redshift 2 is really, really hard. Okay, so if you go back to my plot of, just to show you what I mean. So these are some spectra taken with the NIRSpec spectrograph on the Keck 10-meter telescope. Okay, this is the precursor of the instrument I'm going to tell you about. Here's 0, right? There's no continuum for most of these galaxies, all right? So you can't measure the absorption lines if you don't have the continuum. We're doing better now, but it's challenging. So really basic things, really basic proxies about the stellar population are not so easy to obtain spectroscopically. Most of that stuff is based on photometry. Okay, so let's just recap some of the highlights of what you can learn from the rest frame optical. Okay, so we have our emission line set of O2, H beta, O3, H alpha, nitrogen 2, and sulfur 2. We have our absorption lines, like the Balmer lines here. So for example, here's H delta line. There are also the calcium H and K lines here, magnesium B feature, which is off the edge of the slide, and then the 4,000 angstrom break, which is often probed photometrically, but it's really nice if you can measure it in the spectrum. So these features, I would say form the basis of traditional optical spectroscopy. They yield key insights into the stellar and gaseous contents of galaxies. But the thing is that at redshifts greater than 1.4, which is, as I said, this is the next frontier, the bluest of these, at least of the emission line set, this oxygen 2 line, that moves past 9,000 angstroms, okay? So this becomes a near-infrared problem. And so, if we want to assemble statistical samples of rest frame optical measurements, we really need a transformative boost not only in signal to noise, but also in survey efficiency for near-infrared spectrometers. Okay. The thing that's great is that this has just occurred. Okay? And so there's been a wonderful new development for trying to make these measurements at high redshifts. Okay. So I want to tell you a little bit about the Mossfire spectrograph on the Keck telescopes, the multi-object spectrometer for infrared exploration. The co-PIs of this instrument are Ian McLean at UCLA, one of my colleagues, and then Chuck Steidel at Caltech, who's actually my former thesis advisor. And so with Mossfire, one can do near-infrared. So by near-infrared, I mean 0.9 to 2.5 microns. You can do near-infrared spectroscopy. You can also do imaging. The spectroscopy can be conducted over a 6x3 arc-minute field of view. With Mossfire, you do one band at a time, so there are 4 filters that you can use: the Y band, the J band, the H band, and the K band. These correspond to the windows of atmospheric transmission of the near-infrared. And the thing about Mossfire, okay, so the key thing about Mossfire, then one of the big technological developments, is this multiplexing capability of up to 46 slits at once using this robotic cryogenic configurable slit unit. Okay, so this is wonderful because it means you can make your slit maps basically in real time. It's also bad because it means that you don't have to prepare it. Anyway, so we're looking at some spectra here. Does anyone know what these spectra are of? Of what are these spectra? No, you can't say. What are we looking at?
The sky.
Yeah, it's the sky. Of course, it's the sky. Oh well. Let's see. So the resolution with Mossfire is around 2,300 to 3,300 using this 0.7 arc-second slit, which is what's sort of the right size for these high redshift galaxies. Mossfire was commissioned in the spring of 2012 on the Keck 1 telescope. And it's going to is already enabling measurements of rest frame optical spectra for galaxies at Z of 0.5 up to 5. It's also being used to study things like Lyman alpha at redshift 10. Okay. Sorry. Yeah, so Mossfire has some wonderful things. So it brags a sensitivity boost of at least a factor of 5 relative to the previous Keck near-infrared spectrograph, the NIRS spectrograph. So even if Mossfire were just a long-slit spectrograph, it would still be a great improvement. And so what this means is that in a couple of hours, about 2 hours of integration time, you can attain emission line sensitivities of a few times 10 to the minus 18 ergs per second per centimeter squared. Okay, so that number may not need anything, but what it means is that you can look at star formation rates of about a solar mass per year at redshift 2. Okay, so that's pretty good. And so in practice, even though you can put up to 46 slits on a mask at once, in practice we find that we get something like 30 objects. Okay, so it's maybe not the full promise of 46 objects, but an increase going from NIRSpec where it was 1, maybe 2 if you aligned your long slit between 2 guys. If you're really lucky, you get 3 at a time. Okay, but doing 30 up to 35 sometimes is wonderful. So what this means is that there's an increase in survey efficiency if you take into account the sensitivity boost and the multiplexing factor of more than 2 orders of magnitude. Okay, so this is our transformative boost. Okay, so now once we have this wonderful instrument, what can we do? Okay, so my colleagues and I at the University of California were thinking about this a lot. Given this wonderful new piece of instrumentation, what would be the project to deploy it for? Okay? And so we decided, there were some key requirements for an evolutionary census of the galaxy population at redshifts 1.5 to 3.5, which is that's the next frontier. So what you'd like, ideally, is rest frame optical spectroscopy covering all of the strongest rest frame optical emission and absorption lines between 3,700 and 7,000 angstrom. Remember I said previous work with the near-infrared spectroscopy was over a very limited wavelength range, covering just a couple of features at a time. What we want to do is try to emulate the Sloan survey at much lower signal-to-noise in numbers, but at least the same idea of getting lots of features at a time for any given galaxy. We need a large sample, okay? Now for these redshifts, large means over 1,000. But furthermore, we want to have a sample of galaxies that spans the full diversity of galaxy stellar populations. We don't just want to look at these blue star-forming galaxies. We don't just want to look at galaxies that satisfy a certain type of stellar population. Sorry, we really want to look at a wide range of representative galaxy stellar populations. And furthermore, we want to study evolution, which means that we need to attain multiple redshift bins so that we can look at how things change. And so our project, the Mossfire Deep Evolution Field Survey, MOSDEF, is designed to attain these goals. And so let me tell you a little bit about our people, okay, because we all are working very hard on this, so it's very important to talk about who's involved. So these are we have our photo gallery of all of our co-PIs. So this is Allison Coyle at San Diego, Mariska Creek at Berkeley, Barlow Mobasher at Riverside, Naveen Reddy at Riverside, and then Brian Sayana. If you can't recognize this person, well. And so Brian's also at Riverside. And so these pictures, I think they're really funny, right? Because, for example, to me, it looks like Allison and Brian are posing for their high school ID pictures. And then Naveen and Barham look like they're posing in front, I don't know, the same tree at Riverside or something like that. And then Mariska looks like she's in some fancy magazine, I don't know. So anyway, and then we have a bunch of graduate students at our different, at our institutions. And then another really important part of our project, is that we're going to be collecting these data telling us about the baryonic components of high redshift galaxies. And we feel that it's very important for us to try to compare the observations that we're making with the latest theoretical models. Okay, so we're collaborating with a bunch of theorists who are particularly interested in understanding the stars and gas in galaxies, like James Bullock, Charlie Conroy, Romil Dave, Dushan Karas, and Mark Collins. Most of them are in the University of California as well, but Romil Dave basically works on like every single problem that we are trying to address, so we wanted to, it seems silly not to collaborate with him. Okay, and then we have other collaborators like James Aird at Durham University. Okay, so let me tell you a little bit about our project. So we were awarded what's called a large UC Keck program, or an LMAP program. And so we've been awarded 47 Mossfire nights on the Keck 1 telescope, spanning between the late 2012 through the spring of 2016. We are targeting fields called the Cosmos, Goods North, and Aegis fields. These are the legacy fields where extragalactic astronomers have pooled all of their resources to span the full electromagnetic spectrum and obtain lots and lots of data in the same regions of the sky. In particular, the regions we're targeting overlap with the CANDLES survey, so there's HST rest frame optical imaging of the fields we're targeting, and also the 3D HST survey, so that there are those WIFC3 infrared GRISM spectra of the galaxies in our target fields. We're looking at 3 redshift ranges. I'll justify these in a second, but they're redshift 1.37 to 1.7, 2.09 to 2.61, and 2.95 to 3.8. Okay, so this is about 9 to 9.5 billion years ago, 10 to 10.5, and maybe 11 billion years ago. And so our planned sample is about 500 galaxies at redshift 1.5, 1,000 galaxies at redshift 2.3, and 500 galaxies at 3.4. Okay, let me just explain the numbers here. Turns out that redshift 2 is roughly like the sweet spot for near-infrared spectroscopy, because all the strong emission lines fall in the windows of atmospheric transmission. Redshift 1.5 is kind of like a bridge down to redshift 1 where there's all this information. So that's our main purpose for the lower redshift window. And then redshift 3, there's so little known at redshift 3 that even a sample of 500 galaxies is going to be a huge boost in our knowledge of that redshift range. And one of the key things about our project is that we are selecting galaxies using their H-band magnitudes, okay, so limited in H-band, which corresponds at these redshifts to a rest frame optical luminosity, so that's much more akin to what's done at low redshift. Ultimately, we also want to construct samples that are limited by stellar mass, so that should hopefully even be more representative. And this just shows what our target fields are like. Okay, so this is the Cosmos field, the Goods North field, and the EGS field. And you can see here the gray patches are little regions where the CANDLES survey has obtained J and H band imaging. The cyan circles are little patches where the 3D HST survey is done with GRISM spectroscopy. And then the red rectangles are planned Mossfire masks. And so, as I mentioned before, there's a lot of ancillary multi-wavelength data that have been collected in these legacy fields. There are two other legacy fields, the UDS field and the Good South field. Based on when we're doing the observing only in the spring, we're focusing on these fields. They're spring fields. So there's Hubble data, there's Spitzer, IRAC, and MIPS data, telling us about the stellar population and the dust. There's Chandra X-ray imaging. There's Herschel infrared imaging using the TAPS and SPIRE instruments. There's VLA radio data, and there's a very extensive suite of ground-based multi-wavelength photometry in these fields. There's also existing spectroscopy from various ground-based sources, and also the 3D HST prism survey. So this is really important in terms of targeting some objects where you know exactly what redshifts they have beforehand, so you're not going to fail. But another key part of our project is that the photometry for these fields has been compiled. Well, it's been compiled by many people, but the 3D HST project has compiled all the photometry into really nice catalogs and estimated photometric redshifts for galaxies. And furthermore, once you have all the photometry in one place, it's pretty straightforward to model the stellar populations of these galaxies. So not only are you going to get the spectra, but you'll also be able to estimate things like stellar mass and specific star formation rate and other great things. And this is very key for our targeting, in particular, to have photometric redshifts here, because then we know which objects will be sort of in our target ranges. And so I want to say a little bit about the redshift ranges that we're probing to get that evolutionary census. So we have 3 windows, and these windows are really governed by where the features fall relative to windows of atmospheric transmission. Okay, so you can see, so I said redshift 2.3 is kind of a sweet spot here. You can see that O2 falls in the J band, the O3 and H beta fall in the H band, H alpha, nitrogen 2, sulfur 2 fall in the K band. At redshift 3, we can't get the H alpha and nitrogen 2 because they're redshifted into the thermal infrared, but we can get O3 and H beta in the K band and O2 in the H band. And at redshift 1.5, especially for the red part of the window, we get O2 in the Y band, right around 1 micron, O3 and H beta in the J band, the H alpha, nitrogen 2, and sulfur 2 in the H band. Okay, so we're selecting these redshift ranges to really optimize the detection of rest frame optical emission lines within these windows of atmospheric transmission. Okay, so let me show you some of our data. Okay, so now we get back to that plot from the title slide here. So I'm showing you, remember we take the spectra and 3 different filters for redshift 2, J band, H band, and K band. So you can see here are some examples of redshift 2 J band spectra where wavelength is increasing from left to right, and this is the vertical direction is direction along the slit. Then here's H band, and here's K band. Okay, so the little white blobs here are the emission lines. So here's O2. It's a doublet. Hopefully you can see there are 2 little blobs. The ratio of the strength of these blobs tells you about the electrical density. Then we have the O3, 500, 49, 59. This is H beta. We have H alpha, nitrogen 2, sulfur 2. Split here. And so you can see there's a range of line ratios. There's a range of velocity widths. Morphology here, we even see a pair of interacting galaxies. So one thing, just because it's sort of interesting to discuss the practice of near-infrared spectroscopy, I think it's interesting to discuss the practice of near-infrared spectroscopy. What you see in each case is the white blob and then surrounded by 2 black blobs. Does anyone know what the signature is from, like what we're seeing?
Well, if you were Caltech in the 70s and 80s and working with Jim Gunn, it's AB spectroscopy. So
Yeah,
it's been around a long time.
Yeah, sure.
Optical infrared. So.
Yeah, so basically the sky's so bright that we chop between, we actually do AB, A prime, B prime. It's basically the same idea. We just basically chop between 2 positions and subtract the sky from, you subtract the sky from put the galaxy here, then you move the galaxy over here, okay? Then you subtract this one from this one, and you subtract this one from this one, you get a hole, and then when you register them, you register these things so they line up, you get holes on either side. Okay, so that's the one that you're actually doing spectroscopy. Anyway, and if anyone is familiar with what these near-infrared spectra typically look like, we're pretty happy with how the sky subtraction is going. And then what you do, of course, is you extract the spectra to 1 dimension, and you can see the same features here of the O2 in the J band, the O3 and H beta, the H band, the H alpha, nitrogen 2, and sulfur 2 in the K band. Okay, so these are our spectra. So we had really bad weather last spring during our first sort of key observing season, but the thing is, even with really bad weather, we were still able to do so much better than we could on previous instruments. And so what I'm showing you here is the galaxies that we've targeted so far. Because the weather was so bad, we really decided to focus a lot of our energy on this redshift 2 range, just so we could get some early science out and build up the sample. So you can see here our 3 redshift ranges. Here's the bulk of our sample at redshift 2, where we have about 170 targets. If you look at the properties of the galaxies that we've probed so far, this is a plot of specific star formation rate, so star formation rate versus star formation rate divided by stellar mass as a function of stellar mass. The black data points and the black histograms show basically the parent catalog of galaxies, so everything that we could have targeted down to a given H-band magnitude in the right redshift range, and then the red dots show our actual targets. Okay, so what you can see is that first of all, we're spanning a wide range of specific star formation rates, with things with very high specific star formation rates down to things that are relatively quiescent. And furthermore, we're spanning a pretty wide range of stellar masses, over 2 orders of magnitude, and we are definitely complete relative to the parent sample, down to below 10 to the 10 solar masses. Okay. One of the things that's really wonderful about our project so far is the very high spectroscopic success rate we've enjoyed. Okay, so overall, we are getting 85% of the targets that we put slits on. And if you look at the success rate as a function of AB magnitude in the H-band, okay, so F160W is an H-band filter, the success rate remains above 75% even in the faintest bin that we're targeting at redshift 2. So this is the redshift range where we have the most statistics so far. And in terms of the signal to noise that we're achieving, so this is signal to noise versus H-band flux. So we're achieving signal to noise of 3 for, as I said before, a few times 10 to the minus 18 ergs per second per centimeter squared in the K-band with 2-hour exposure times, and that corresponds to star formation rates of about 1 solar mass per year at redshift 2. Okay. So we're pretty pleased with these sample statistics so far, especially with the success rate, how many slits we're getting something useful on.
What do you do with the slits that we don't have galaxies on?
What do we do with the slits that we don't have
You
yet?
can have a certain number of slits. You said the number of galaxies is less than the number of available slits.
Oh, so the way that this configurable slit unit works is that there are 46 pairs of bars. Okay, so each pair of bar, so in principle you could make 46 independent slits. Sometimes though, the galaxy, because it's not like you mill the slit mask at arbitrary Y positions in the mask, these bars are fixed. So sometimes you actually need to allocate more than one bar to a pair of bars to a galaxy. So sometimes we have longer slits.
So you're utilizing all the slits you can.
Oh, sure. Yeah. We use everything that we can. So the other thing that we do is that in a given redshift range, so we have masks that are primarily redshift 2 masks, but in case we have gaps, then we fill those masks with either redshift 3 or redshift 1.5 targets, because you'll get something useful for these other redshift ranges. Yeah. Okay, so now with all these great data, there's a lot of very exciting science questions that we can address. Okay, so we're very interested, and more. Okay, but these are some of the areas that we've outlined that we want to pursue. Okay, so we want to understand star formation and the growth of galaxies. We want to understand dust attenuation in galaxies at these early times, the metal content and physical conditions in galaxies. By physical conditions, I mean what's the density and pressure and ionization parameter in the regions in which stars are forming, because these are very key observables to obtain, and they might have some important implications. We want to study the cycle of baryons. What does that mean? We want to understand how gas gets out of and into galaxies. We want to look at the dynamical masses and structural evolution of galaxies, because of course, every single galaxy for which we obtain a spectrum has an HST image in the rest frame optical, and also in most of the rest frame UV. Okay, so we can really look at the structural evolution of these galaxies. And as I'll describe, we can also look at the properties of active galactic nuclei in our sample and the coevolution of black holes and galaxies. So in the last part of the talk, what I want to do is I just want to give you some teasers of some of the areas that we are working on right now with our early science data. And I apologize for the in-progress version of some of the plots that I'm showing. Some of them are a little bit more polished than others. Okay, so as I mentioned, we're very interested in studying star formation and the growth of galaxies. So what you can see here is this plot from Voigt et al. It's a plot of the star formation rate versus stellar mass of galaxies in different redshift ranges, and remember I showed this plot before. This concentration of galaxies of star-forming galaxies along what looks to be a somewhat a indicator correlation in log space here is often termed this main sequence of galaxy evolution. The fact that the star formation rate appears to be correlated with stellar mass, with less scatter than astronomers expected. Now, the thing is, astronomers are trying to measure the evolution and the normalization of this relationship, so how much the star formation rates evolve for galaxies at given stellar mass, the slope of the relation, and also the scatter. But the problem is that most previous samples are either based on photometry only, or if they are spectroscopically confirmed samples, okay, so photometry only where you don't actually have an actual redshift for the galaxies, so that's one limitation. Or else the samples are spectroscopic, but they're very incomplete. They're really limited to very high mass galaxies or UV selected galaxies or a particular type of galaxies. Furthermore, most versions of this plot only use the rest frame ultraviolet luminosity or a fit to the stellar population to estimate the star formation rate. So I would argue that the H-alpha luminosity is a much more direct probe of the instantaneous rate of star formation. Okay? And this is really important because if you can measure the star formation rate average over much shorter timescales, as you can do with the H-alpha line, you can really get much more of a sense of the true scatter in this relationship. Okay? And look for deviations from this so-called main sequence of star formation due to shorter timescale events, like ruptures or when the star formation would be elevated over a shorter timescale. And so this is what we are doing right now. Okay, again, I said this is a very early version of this plot, but we can measure the star formation rate from dust-corrected H-alpha emission from our sample versus stellar mass, also measured from our sample. And it's an early version of the plot, but we're going to be able to make this plot, I think, in a much more powerful way than previously. Yeah.
Could you give us an estimate of what the uncertainties would be in those measurements?
Oh yeah, so I mean it's a question. Well, the line flux uncertainties would be negligible, but the uncertainties in the dust extinction might be a factor of a couple or something. And then there's a question about the IMF. There's but I'd say it's probably a factor of a couple. Now the other thing that's really interesting is that because we have both the H-alpha luminosity and the UV luminosity, because of all the multi-wavelength photometry we have, we can actually try to make comparisons between the star formation rate estimated from the UV and the H-alpha lines. And this might shed some really interesting light on the star formation histories of the galaxies. If a star formation rate indicator that's average over longer time scales, like the UV, if you compare it to the star formation rate estimated from the H-alpha, that might actually tell you some interesting things about the recent history of star formation. Furthermore, it could also tell you stuff about the high mass end of the IMF, because there are different predictions for the ratio between this UV and H-alpha luminosity. Now the other thing that's also really important, this is just sort of a practical thing, but the problem, if you don't have spectroscopy, is that you're measuring photometry for galaxies where the photometric bands are actually contaminated by emission lines. For example, H-alpha shows up in the K band at redshift 2. If you don't correct your photometry for these strong emission lines, you might have some biases that result in the stellar population parameters that you infer, like stellar mass. Okay? So because we have both photometry and the spectroscopy of these emission lines, we'll be able to obtain much more clean estimates of the stellar population parameters like stellar mass. So something else that's a really important question in understanding these high redshift galaxies is what's the nature of dust attenuation? Okay? So the vast majority of estimates of dust extinction at high redshift are based on either just looking at the rest frame ultraviolet color, inferring something about the intrinsic rest frame UV color, comparing it with the observed one and saying, oh, that's how much dust extinction there is, or else fitting the spectral energy distribution with the stellar population model and inferring the dust extinction that way. Now, if we want to use the H-alpha line for estimates of the star formation rate, we really need robust estimates of the nebular extinction. Remember the comparison of the H-alpha to H-beta line fluxes. That'll tell us directly about how much dust there is in the star forming regions. Now, there's been a lot of debate about the nature of nebular extinction at redshift 2 and redshift 3. Okay, so the question is, do the H2 regions suffer the same amount of extinction as the massive stars? There's some evidence in the local universe that the H2 regions are more attenuated than the massive stars. Okay, they're more embedded in dust. And this is work from Danielle and Calzetti studying local starburst galaxies. And there's been a lot of debate at redshift 2 about whether or not the H2 regions have the same EB minus V as the stars. Different authors have found different results about whether EB minus V gas is the same as EB minus V stars. And so we need to know this, okay? We need to understand how to correct our H-alpha emission lines. And so we've made an early plot of the nebular extinction, so inferred from the Balmer emission line ratios versus the stellar extinction. And this is, the dashed line would be a plot of 1-to-1. This would be the same attenuation for gas and stars. This is where our data points lie. And the dotted line here is what's inferred for local starbursts, that the H2 regions suffer more extinction than the stars, okay? And so this would be a very important measurement to make just for understanding how to correct H alpha emission in general. When you don't have rest frame optical spectroscopy, we have lots of lines. And this also might tell us something interesting about the geometry of dust and gas in these early galaxies. Okay, so I just have a couple more things that I want to tell you about. So one of the other things that we're pursuing is the metal content of these high redshift galaxies. So the metal content of galaxies reflects the past integral of star formation, okay, so the enrichment of the gas by past epochs of star formation, modified by gas inflow and gas outflow. And so these gas phase oxygen abundances, they're very meaningful when you consider them together with the masses of galaxies, and also the stellar masses and the gas masses, and also the star formation rates of galaxies. This is when you make the comparison of all these things together, you can actually try to say something about gas flows. And so this here on the left, this is a plot from Tremonti et al. 2004, showing the gas phase oxygen abundance versus stellar mass. You can see there's a correlation here. Now, one of the things that's also been inferred for galaxies in the local universe is that when you plot oxygen abundance versus stellar mass, but then you take into account star formation rate as a third variable, you actually see some interesting systematics, okay? So if you look at more highly star-forming galaxies, the purple to blue to red is higher star formation rate to lower star formation rate, you see that there's systematic variation. At a fixed stellar mass, more highly star-forming galaxies have lower gas phase oxygen abundance, so consistent with higher gas fractions. Now, this is great, okay? It's wonderful that we have these measurements of 50,000 galaxies in the local universe. But when you go to higher redshift, you know, the samples of objects with such measurements of the oxygen abundance versus stellar mass are really tiny, okay? So, for example, okay, so in each one of these plots we have the blue curve, which is the Sloan galaxies. At redshift 2, this represents a sample of about 100 galaxies from Erb et al., but each one of these plots is actually a composite spectrum. Okay, so the data points for redshift 2 mask the true variation here and the true scatter. What you really want to know is the slope, the normalization, and the scatter of this relationship. Now, redshift 3, there are about 10 data points. Okay, so really that field is wide open. Okay, we really have a lot to learn about this. And so that's one of the key things that we're trying to measure in our sample, is we're trying to measure the gas phase oxygen abundance so far at redshift 2. We want to do it in an evolutionary sense eventually, but right now we're doing it at redshift 2. So we've estimated metallicities just based on that simple indicator, the nitrogen 2 to H alpha line, and plotted them on the same plots as the Sloan data, okay, using the same indicator, okay, so, and in fact, we've used two different translations between the empirical line ratio and the physical quantity, the oxygen abundance. And I guess the main thing that we find, which has been found before, which is that here you have oxygen abundance versus stellar mass, okay, so at fixed stellar mass, here are the local points, and then here are the redshift 2 points, so both the black data points and the arrows are the individual points. And you can see that, you know, at fixed stellar mass, at higher redshift, you evolve towards lower metallicity. Now, one of the things that's great about having all these individual measurements is that we can actually try to start probing the scatter in this mass metallicity relationship. Furthermore, because of the way that we selected our sample, we should have a much more representative set of galaxies at redshift 2 than previous work. These points from Erb et al., these cyan crosses here, which are just for this UV selected sample. Now,
I can't see the axis here. Offset is 0.3 or 0.4 dex.
yeah.
So galaxies have evolved a factor of 2 in oxygen, only a factor of 2 in 10 billion years.
Mm-hmm. Well, galaxies at fixed stellar mass, so it's not the same galaxy, right? Because galaxies would move in diagonal ways. But yeah, but at fixed stellar mass. Yeah. I mean, the other thing to take away from this is that at these early times, galaxies are fairly enriched. So, yeah. Okay, now one of the things that's kind of troubling, and one of the things that we're working very hard right now on, is that whether or not there's this so-called fundamental metallicity relationship, which is that relationship among mass, metallicity, and star formation rate. So whether or not we infer this offset towards lower metallicity for the higher star formation rate galaxies depends on which indicator we use for metallicity. Okay, so this is really troubling. Okay, so if we use this translation between the empirical N2 to H alpha and oxygen abundance from Myelino et al., you can see the more rapidly star-forming galaxies with the blue points, the more quiescent galaxies with the red points. There's this nice separation between more star-forming and less star-forming galaxies. But if we use this other indicator from Bpt et al., the situation is much more murkier. Okay, so anything that depends on which proxy you have for oxygen abundance, is not a very robust result. Okay, but furthermore, there may be a much more fundamental problem about inferring the metallicities of galaxies. Okay, so I'm almost done. I just want to say like a couple more really quick things. Okay, because we started a little late. Okay, so there may be a problem even with just using these indicators of oxygen abundance, because it may be that the conditions in the star-forming regions at high redshift are systematically different from those in local star-forming galaxies, and you can't just apply these indicators of metallicity blindly at high redshift. Okay, so let me show you what I mean. So we have what we call this Bpt diagram of O3 to H beta versus N2 to H alpha. This is for the local universe for Sloan. Okay, and these diagnostic line ratios are used to basically discriminate between star-forming galaxies, which fall along this sequence of increasing metallicity, and then AGNs and liner galaxies up here. And what's really interesting is that when our early measurements of star-forming galaxies at redshifts greater than 1 showed some systematic offsets in the locations of galaxies in this diagram relative to the locations of local galaxies. Okay, so here's a plot from Brinkman et al. Where we have the local star-forming sequence. Okay, and then here these individual data points are our high redshift galaxies. Okay, so it looks like there's some kind of systematic difference between the properties of these high redshift galaxies and the low redshift galaxies. Now the thing is, the number of galaxies at this earlier time, several years ago, was so small that we thought, oh, maybe we just got unlucky and these first galaxies were weird. But one of the things that I'm most excited about is now we have a statistical sample at redshift 2 from this MOSDEF survey. Okay, and you can see our Bpt diagram. So here's the Sloan sample, the star-forming sequence, and then the red points are our sample. Okay, and so you can see that definitely there is still this systematic offset between the redshift 2 galaxies and the Sloan galaxies. Okay, and so it suggests that this offset is real. So if the line ratios are different in these high redshift galaxies, it suggests differences in the physical conditions in the high redshift galaxies. Perhaps there's a higher ionization parameter, a harder ionizing radiation field. And with MOSDEF, we're going to isolate the factors that lead to this offset. We want to understand exactly why these high redshift galaxies look different. Because if we can understand why the high redshift galaxies look different, then it will be possible to make new metallicity indicators for our empirical line ratios to go to the physical property of oxygen abundance, which is what we really need to do. Okay, so this is another really important avenue of research. Okay, I think I'm going to skip over what we're learning about AGN activity. That's something else that we're going to work on a lot, is how well we can discriminate between star-forming galaxies and AGNs. The thing I want to leave you with is what we're doing, trying to address stellar absorption line studies. Okay, so as I mentioned before, the current sample of galaxies of redshift 1.5 with continuum and stellar absorption detections is less than 10 objects. Now we detect continuum for our brightest targets. For example, this object Cosmos 11982 at Z of 2.09. So here's our J-band spectrum, our H-band spectrum, and our K-band spectrum. You see the signal noise is about 10 here. And what's great is not only do we detect continuum for this object, we also detect stellar absorption lines. So here we're zooming in on that object, and you can see the calcium H and K stellar absorption lines. Okay, so this is going to allow us to make detailed comparisons with stellar population models for galaxies like this, to infer the star formation histories, much more detailed than we can with just photometry. We'll get robust estimates of the dynamical mass combined with our HST imaging, and perhaps we'll be able to even look at the stellar metallicity, not just the gas phase oxygen abundance. Now for fainter galaxies where we don't have such nice detections for individual objects, we'll try to stack them to get statistical detections. So we're really excited about this aspect of the project. Okay, so let me just summarize. Hopefully what I've shown you today is that we've entered into a new regime for rest-frame optical spectroscopy of the distant universe. It's now possible to obtain robust statistical samples of the gaseous and stellar contents of galaxies at redshifts greater than 1. With my collaborators, we're conducting this MOSDEF survey using this wonderful new instrument, MOSFIRE on Keck. And so the survey is it's leveraging this multi-wavelength data sets in these legacy fields like Cosmos, Aegis, and goods north, and we hope to address many key questions in galaxy formation, such as the star formation and assembly histories of galaxies, their dynamical and structural properties, the evolution of dust and metals in galaxies, the physical conditions in H2 regions in which stars are forming, how gas gets into and out of galaxies, and also the evolution of AGM activity. So the surveys commenced. We're really in the middle of our early science. We're in the middle of making masks for our next observing runs, which start tomorrow night. So we're very excited about the project, and so I hope you'll stay tuned for lots of new results from our team. Okay, thanks.
Questions?
So there was a plot where you showed the evolution of oxygen abundance versus mass and how that changes with redshift. That, yeah, or actually the next slide I think where it showed.
Yeah.
So in the redshift 0 one, it's a relatively tight-ish relation.
Right.
But then in the plot here, it's scattered down, but you still have galaxies that seem to fall in a local relation. Is that increased scatter something that you believe at this stage, or is it still sort of a bit in the don't know phase?
Yeah, no, I think we're still trying to figure out exactly what's going on. I mean, of course, the measurement errors are larger for our galaxy, so that's one thing I think we need to quantify what the intrinsic scatter is relative to the fit and compare that with the phone. So we haven't done that detailed analysis, but it's really what we're trying to do. It's basically once you account for the measurement errors, what does the scatter look like? But there's another whole issue, which is basically the systematic error of going from the empirical line ratio to the oxygen abundance. Now, the question is, how does that error, how does that scatter compare between the local universe and the high redshift? Now, in the local universe, we have some estimate of that because people have measured the direct oxygen abundance for H2, based on that 4363 oxygen line, where you actually have like the real oxygen abundance, and made a plot of that versus the empirical line indicator, just the nitrogen 2 H alpha. So we know what the scatter is for the local galaxies. The problem is we're not going to get those 4363 measurements for the redshift 2 galaxies. So it's going to be difficult to understand what the systematic uncertainty is for the calibration of the redshift. So that may be a limitation. But we can at least look at how what the intrinsic scatter is once we account for our measurement errors. So we'll do that. And then we'll also be trying to understand how the scatter is correlated with the other galaxy properties. That's one of the nice powers of our project, is that we don't just have the Mossfire spectra, we have all this other information. So we can see other systematics within the relation as a function of the properties.
We should really let you get some lunch.
Oh, okay. I'm sorry I went on so long.
No,
Sorry.
no.
So,
I forgot.
any other questions?
But Alice will be here the rest of the day, and I think maybe scheduled to talk to her, and if you want to get in schedule, just come and talk to me as well. Thank you, Alice.
Thanks a lot.